electric freight goes faster than diesel freight. You can accommodate longer trains. If you've ever been stuck on a slow-moving passenger train and a train manager or a guard has announced, sorry, we're stuck behind a slow-moving freight train, inevitably that would have been a diesel freight train. And by having faster freight trains, we also allow to accommodate more passenger trains. There are sustainability benefits, so quieter trains, less pollution at the point of use. There is, however, the embodied carbon in construction, but conversely a carbon saving when you remove diesel trains. But when we look at what's the embodied carbon in building masts and foundations compared to what's the payback by removing diesel trains, there's a really quick payback time of typically 3 to 4 years on Midland Main Line that's being very slowly electrified. It's just under 3 years. So there's lots of reasons we electrify. I wrote or co-authored the Why Rail Electrification report for the Rail Industry Association, who were here yesterday, which goes through lots of the research that backs up those facts. So if you're bored and ever want to read, there's a QR code there. We also did a very short version for government, which is the top one because they would never read a 200-page report. So we did a single A4 piece of paper for them. But yeah, just Google it on the RIA website or yeah, use the QR codes. But yeah, what are the issues with rail electrification? And the hydrogen presenter earlier, yeah, kind of nailed it with it's the upfront capital cost. And over the years, the government have on many occasions said, yes, we're going to do more electrification for all the reasons I outlined. But then at some point, yeah, realised what the costs were going to be and decided to scale back, or costs increased beyond expectations and they scaled back. And yeah, not all of you will remember, but yeah, the photos at the bottom are of Chris Grayling, who was the Transport Secretary during the last round of large electrification cancellations. But yeah, costs are an issue with electrification, but there are two important caveats with that. One is electric railways are cheaper to operate than diesel railways, so there is an upfront capital cost. However, diesel trains are more expensive to buy, they're more expensive to maintain, they're more expensive to provide fuel for. So over the life of an asset, it's much cheaper to run an electric railway. So again, there is a payback time way before the end of life. So over a lifetime of an asset, it's much cheaper to run an electric railway, even with those capital costs. With capital costs, I work for an engineering company in an engineering-led industry. So we often focus on engineering issues. So we look at how we can fettle the engineering to cut some costs. But with the costs, we need to put that in a wider context. So the speaker earlier talked about 2.8 million a kilometre to via Great Western, and costs have come down a lot since then, but they're still high. But on Great Western and some of the more recent projects, the costs of things that I think of that are linked to engineering, so design, materials, construction, are only a small part of the costs. So on the current Midland Main Line project, those things represent about 21% of the cost of electrification. So on that Midland Main, on Great Western, 2.8 million a kilometre, well, actually only about 600,000 of the electrification costs is electrification. A huge portion of that is access charges, so payments to train operating companies not to run trains. And that's quite unique to the UK, the way our industry is structured. A significant proportion is project management offices and other white collar, not design or engineering based costs. So yeah, the actual cost of electrification is only about 600,000 a kilometre in the UK. But yeah, Here is a common issue, and this is a fairly crude sketch we often face in the UK, and one of the things that can drive costs. So you have what would have been an unelectrified railway. You want to electrify it. It's often built in Victorian times or the 1920s. That would have had a low bridge to get passengers between platforms. No one would have considered electrification at the time, so it's really low. Nearby, you may have a level crossing to allow cars to access the station, and now you want to come and electrify it. So you've got to snake your electrification wires under the bridge, and you need to allow electrical clearances, and then you need to go high over the level crossing because you might have lorries or double deckers, and you need electrical clearances again, and you don't want wires to be brought down by high vehicles. Now, if you think of a train coming on perhaps a fast platform at 100 miles an hour with its pantograph, once that's electrified, and where the forces are in that pantograph, it's now being forced down under that low bridge and up again over the level crossing, and that's not where the pantograph wants to go. And there's risks of maintenance issues and poor current collection. So historically, based on the rules we had, we often ended up raising bridges. And a huge portion of Great Western electrification costs was actually lifting bridges, just to give clearances and to give remove gradients. And a lot of those calculations are based on essentially work done in the 1950s and using methods that we definitely would not use nowadays. So a huge part of our work has been, well, if we were to apply everything we've learned now, how would that be different? Would we still need to raise the bridge? Another common issue we have is the distance between structures. If you can have a 50-metre, move a 50-metre span between structures to 60 metres or 70 metres, it can have a massive impact on the cost. But how we calculate wind loads, how we calculate how wind moves the wires, again, it was historically based on very old calculations and really didn't take a risk-based approach. So we ended up building more structures than perhaps was optimal. I was discussing my rubbish ChatGPT picture earlier with David at the break. So I'd asked ChatGPT to, because I was short of an image, to summarize the presentation in a comedic single photo, which has then led me to use it for the title, which I think it's trying to say it's a maths sandwich within business bread. But perhaps that is, I'm starting off with the business issues. Sam's going to do the maths bit, and then I'll feed back into how it's then fed back into the business. But I've been dealing with the output of research in rail for about 25 years, and maybe the past 10, I've also been giving some of the inputs into that. But often, historically, and we've got a lot better, the people who have a problem, that doesn't always align with the people who are doing the research. What my problem is often didn't historically align with the research, and that's changed a lot. Railways are massive systems, and there's been a lot of talk of silo working, and that historically has been a massive problem, not just between academia and businesses and industry, but also between track signalling, electrification, etc. And the biggest impact that's had historically is we don't trust people enough to share data, and that has come along a lot, but it is still a big issue. Real world does not always align with the controlled conditions of the models and simulations we do often doesn't align historically with the real world. So the human factors. I was in a standards workshop maybe 10 years ago with the German train operator, and we were discussing droppers, which I think someone described earlier. So the connection between catenary and contact wire, and the German railways were adamant that the output of the calculations show the length of droppers to the nearest tenth of a millimetre. and everyone else was saying, well, you can't install to a 1/10 of a millimetre. Most installations done at night, 6 meters up in a basket, in poor lighting conditions, often in wind and rain and snow, with someone who just wants to go home because it's freezing. They are never going to install to a 1/10 of a millimetre. But the people who had done the research for German railways were adamant, well, no, my calculation shows it needs to be installed to a 1/10 of a millimetre for optimal performance. And again, but that human factor has improved dramatically over the past few years. Research historically has been inaccessible to those outside research, so it just goes into a journal that I cannot access, which is why events like this are really important to share the knowledge. So yeah, thanks to the organisers. And yeah, my last comment on this slide is, which is again something I was discussing at the break with some people, was for the time you have an idea for some research, to doing the research, to having some recommendations, and that then going into change standards is a very long time. For some of the projects we've been working on, it's almost 10 years, and people go, particularly people who might be changing the standards. So by the time you've done the research, the person who wanted the research has left. One of my favourite quotes is from William Burroughs in Naked Lunch, where he said, you weren't here at the beginning, you won't be here at the end, so all your knowledge can only be superficial. But again, I think events like this are really key. If we can share knowledge, even if I know who to speak to when I have a problem because I know someone studying it, that is already a massive improvement. So yeah, this is my last slide before I hand over to Sam to go into some detail. But I wanted to give an overarching timeline of what we've been doing, in particular to solve that gradient issue I showed you at the station. So I'm going to try not to steal too much of your thunder. But yeah, after Great Western electrification, we realised there was a big issue with the way we calculate gradients, that it was producing results that cost an incredible amount of money. In some countries, Felix has gone, but in Switzerland, where he's travelling to now, they would just spend the money and raise the bridge. But in the UK, our purse strings are a little tighter. So yeah, in 2015, we had the idea we need to do some research into this. So with David at Sheffield, whose I think original idea it was, with Network Rail and us doing funding, with also some EU funding, we developed the PhD, which Sam turned into you. And that really got us to understand, what were the opportunities, how it works, and how far wrong we were going. That then led, once the PhD was complete, we carried on working with Sheffield, the RSSB and Network Rail. With RSSB, one of the historic issues they had was introducing new trains. So every train performs differently. So if you think trains have different pantographs, they might have 1 pantograph, 2 pantographs, 3 pantographs. Those pantographs might be at different spacings. Overlaid onto that are different electrification systems with different tensions, and it creates a lot of complexity of performance. Different systems perform differently with different combinations of pantographs. And what train operators have been doing up until that point is modelling every new train they wanted to introduce on every specific route they wanted to introduce it. So building on what we learned in the PhD, we actually created simple ways that train operators could know upfront, will my train work on this electrification system from a dynamic perspective. We also then built on that with Network Rail to work with them to change their standards on how they calculate gradients for bridges and what's allowable and where they don't need to raise a bridge. Building on that knowledge, Sam moved over to Frey to work for us directly when that research finished. And we've since been working with Network Rail on how they reduce costs by, again, optimising that system built on the models and maths we developed as part of the PhD. And that's now being used on real upcoming electrification projects. So when they're doing the business case, looking at what system they use and how they optimise it to minimise the cash. But we still had an issue that whatever line we looked at, there was always some bespoke problem we'd never come across before. And how do we know our models and tools worked in those situations? So that's the current live project we're working on, and that was funded by the Department of Business and Trade at the new Welsh test track being built, GCRE.
Over to you, Sam.
Yeah. Afternoon, everyone. Yeah, so mine is more of a whistle-stop tour through where I started, where I've ended up, which is here today, talking to you guys. I am going to give you all a quiz and see if anyone can put their hand up and name what either of the equation on the left or the equation on the right represent. Anyone? Yeah. It is, yeah. On the right? No, they are the Lorentz equations. Some of you may have heard of the butterfly effect. This is where they come from because that graph looks like a butterfly's wings. This was a very early model of convection in the atmosphere. So yeah, my research life started out with looking at things like this. This was part of my master's year during undergrad. So I had an emphasis on applied maths, hated pure maths. I didn't care about infinitely dimensioned systems. So mechanics, fluid dynamics, and dynamical systems were my focus. And then final year project was focused on numerical modeling, which is where I started thinking about what I want to do with my life. How do I apply maths that isn't just sitting in a room by yourself with a piece of paper and hoping something comes of it in 20 years' time. So after that, I moved on to my PhD. I think a bit like Steve was talking about yesterday, riding the wave. I had no idea what to do before I graduated. I saw an advert for a PhD that paid £6,000 more than it normally did, and went, cool, I'll apply and we'll see what happens. Interviewed the day before I graduated, offered it the day after I graduated, and like, that's the next 4 years sorted. Great. I like to fall on my feet. So it was focused on dynamic modeling and the fluid dynamics of contact wires. The main issue, I think, as Noel mentioned, was what happens when stuff is getting in the way? How do we reduce that capital cost of electrification when there's a bridge, a level crossing, whatever's getting there that means you can't do what you really want to do, which is a nice flat wire with no problems in the world. Imagine if we could do that. So did lots of testing through dynamic modeling. Currently, we can grade a contact wire at 1 in 625. For large height changes between a level crossing and a bridge, this means we can need up to 1 kilometre of space. That's not always possible. If we take a station, for example, there's going to be a footbridge and there may be a level crossing within 200 metres of it. We're never going to get the height change that we want. So yeah, as I said, there's probably going to be something in the way. So if we can introduce these steeper gradients, we can get the height change, we can avoid expensive civil changes. And I think that graph under there makes it really obvious just how dramatic an effect this can be, with cutting off 1 kilometre of space needed to get this 1.2 metre height change, something like that. So yeah, we modelled this case, lots of different cases over lots of different types of overhead line. The main issue is you are accelerating that pantograph head. It doesn't want to change direction. You're telling it, I've got to go down, I've got to go up. It's probably going to have some spiky contact forces. If you accelerate something, you get force. Turns out it's only about 14% more contact force. Really simplistically, we could look at a wear equation. That may only be 14% more wear. We never really got into when that wear regime might change, but it's hopefully going in the right direction of we can maybe push these rules on what we can do. So yeah, as I said, steeper gradients are unlikely to be a really bad thing unless you are dangerously overspeeding and your pan slides off the end of the bottom. Yeah, real world testing at GCRE. I'm not going to steal your thunder for later. So, finished my PhD, became an RA for 2 years, 2 major projects, both on electrification. There was also a bit of time looking at passenger movement in COVID, but we'll not go into that here. So yeah, RSSB, this is characterizing different kinds of overhead line and pantograph combinations. We built an obstacle course. This is representative of what a line might look like after electrification. There's a couple of bridges, a level crossing, and some overlaps between different lengths of wire. All the kind of normal things you would expect. Between all the different pan types, train types that currently run on GB main lines, there's 144 different combinations. And so we ran all of those through the obstacle course from speeds between 60 and 125 miles an hour. It was a big project with a lot of simulations. And then there was also Network Rail's bridge optimization project. When you get to a bridge, typically to meet clearances, we will reduce the height between the catenary and contact wires. And obviously you can't do that in one big jump. We've got to grade it down slowly. So this is a typical drawing for an approach to a bridge. And you can see in the middle there, we've got a 30 mil height difference between the catenary and contact wire. Over on the right, where H is, that would normally be 1.3 meters. So what we wanted to look at was, is that the best way to do it? Or can we make that 30 mil 0? Or do we just, or is it really, really bad to do either of those things and actually we need a bigger gap? So just a bit of detail on the RSSB project. As I was saying, these are all the combinations that we modeled that are in the dark green. Yellow, we already knew about. Pink and grey, we're out of scope or we weren't worried about. And this was the compatibility matrix that it ended up being called for all the different pan types, all the different types of overhead line that said, I can run this pan on this line in this combination up to this speed. And so anybody could look up this chart and say, I want to run this class 730 on a Great Eastern line, which you've never done before. What speed can I go to? So yeah, as I said, large range of reference cases now exist. We just look at the table and go, no, that doesn't work. Yes, that does. Feasibility of lots of different combinations are known. They weren't known before, particularly for multi-pantograph operation. Lots of single pan stuff is known, and it's pretty easy because you only have one pan, one wire wave. It carries on as normal. Short-term substitutions can now be done if, as I hope, we'll start electrifying more and more places. When we need to reroute trains for diversions, we don't have to worry about making sure that it's a viable thing to do, and we could maybe get rid of some bi-modes. After that, Alstom wanted us to do the same thing on their new trains, the Class 730s, for 3-pan operation on West Coast Main Line. They were introducing them 2022-ish, something like that. But Network Rail weren't prepared to just say yes without us doing some testing. So we did that. We said you can do 110 miles an hour, which is what they asked for, happily. Also, of course, was then shared with industry and academia for them to use. That any of you building overhead line models and want to know what the geometry looks like, you can go and look it up. It's really available to anyone. And it's pretty useful because it uses different cases compared to validation techniques that we used to use. So in the validation cases, they would never have bridges or level crossings. Now you can go and find some data and use it that does. So going back to the bridges part of the work I did for Network Rail, the outcome of that was one case that we looked at was fine as is. They didn't need to change anything. The other case was we need to update the drawing. And you can see on this one, compared to the drawing I showed you earlier, we've removed that 30 mil height difference. We can go all the way down and run it as a double contact wire underneath the bridge. And I'm quite proud to say there is a Network Rail drawing with my signature on it now. The person who did maths would never have expected that. So yeah, that was the end of my time at Sheffield. Then I moved over to Frey in 2022, just before Christmas. Nice little present. And looked at two major things so far: optimizing UK Master Series electrification and optimizing carry-wire neutral sections. I'm not even going to try and explain what a carry-wire neutral section is in the time we've got, other than that it's a bunch of overlaps. And then also I kind of dip in and out of other projects that other people are working on to kind of help out on the math side of things. So I do statistical analysis, looking at UK wind speeds and what's the risk of flashing over infrastructure. So optimizing UKMS. This was quite a big project. It was a year long, looking at how do we reduce the capital cost of electrification. As Noel said, it's only about 20% of the entire thing, but we need to make the savings where we can if we're going to convince anybody to keep building it. But also not just reducing the cost as an outright aim. What improvements can we actually make that are just going to be beneficial anyway? Because at the moment we've got UKMS 100 and UKMS 125. Could we actually do anything with either of those systems that's going to improve them without having to spend £10 million updating anything? Well, first thing, easy cost reduction is make your span lengths longer. If I've got fewer structures, less steel, that's less money. It's also less carbon. So it's a really big benefit to push out those span lengths. UKMS at the time when we started this project could do 63 or 74 metre spans depending on the tension. Up to now, the current maximum is 95 metres. They tested that on Midland Main Line November.
Yeah, not long before Christmas.
Yeah, and it worked. Did they take it down afterwards?
Yes, they did. Yeah, it was only for test.
Yeah, cool. But yeah, so you could go to 95 metres now if you could actually find somewhere to put a span in where that worked. As I'm going to explain now, you might want to do 95 metres, doesn't mean you always can. If we just look at span length, that really simple equation from the 1960s that tells you what is the maximum span I can have at a given location. Now, just from that, there is 1, 2, 3, 4, 5, 6 things that are going into it, but each one of those things has got 3 or 4 things feeding into it. So how do we work out what is the maximum span length? Well, we could try and do everything individually by hand every single time, or do we just look at every possible combination we could have inside a tool that will spit out the best thing that we should use? So we did that. I'm not going into the detail of how the tool works today, but we assessed approximately 12,000 different kinds of overhead line, comparing them to the 2 that we currently use on new UK electrification. I think so. There's some easy wins that we learned from this, that we said to Network Rail, you should just go and do this now. One of those was get rid of UKMS 100. We've got 2 types of equipment. Get rid of what they thought was the cheaper one. Yeah, turns out not so much. Just stick with the UKMS 125. Even though it has a higher tension, you are saving money by having these longer span lengths. Adopting larger system heights. Currently we use 1.3 meters. We could go to 1.8 or 2 meters. Again, that can increase the span lengths, getting costs down. There are also some longer term recommendations. There are lots of rules within designing UKMS about, I've got a minimum 500mm dropper length at the middle of the span. Is that rule really necessary? The idea is that it'll give you some good dynamic performance, but that was a rule dreamt up one day, as far as we know. Nobody did the testing to prove that that is what we should use. But then also looking at different things that you wouldn't include in a normal system: aluminium conductors, smaller contact wires, or using offset catenary. So there's lots of different little things that you could do to UKMS to get the cost down. So yeah, can we do things better? Well, we did a case study. The shops line runs from Edinburgh to Glasgow. We looked at 36 kilometers of the route, and what could we do using all these little tweaks to different parameters, move those structures around? Could we save any money? Because it was a newly electrified line at the time. I think it was in 2019. They used 730 structures on the 36 kilometers of line we assessed. If we just tweaked a few things, followed the rules as they existed at the time, we could get it down to 644 structures. The capital cost saving just by doing that was £5 million. And we didn't change any of the rules in UKMS. We just followed them as they were written down. So we're currently working on the same ideas to other lines around the UK, and taking everything we learned from this project to applying it to new electrification, not just seeing what happened to old electrification. So moving away from a global overview of all the different parameters of an overhead line, we'll look at just wind in this case. So Network Rail wanted us to assess the accuracy of how we calculate wind speeds. But at the moment, it's 72. That's based on a 1991 standard with our specific annex. So we looked at 40 weather stations across the UK that are shown there on the map with 50 years of wind data, hourly data. It was a lot to get through. And then tried to do either a statistical analysis on this data and compare it with the measured data from all these wind stations, see do they actually line up. Because getting the wind wrong means we get dewirements, and they are not great. Or you can be coming out of Paddington, which dewires, I would say, every 6 months at the minute. So are we getting the counts right? Turns out, on average, yes, it's about okay. In really extreme locations of the UK, on the coast, where the wind speeds are significantly higher than inland, it's not as accurate. But it's unlikely that we are going to be electrifying the Outer Hebrides anytime soon. So I wouldn't worry about that right now. So yeah, you can see on here, we've got the 3-year and 50-year return speeds, and the grey and orange lines are what's the calculated and measured speeds, and the black line is how accurate or inaccurate they were. So yeah, worst case is between minus 30% up to 40% difference between the two values, but for the most part, they're within plus or minus 10%. So moving on, to carrier wire neutral sections. As I said, I'm not going to explain exactly how they work, but as a schematic there, they are 4 overlaps in a row, and the idea is to separate the electrical phases of the AC system. The problem with them is it's 4 overlaps, and they can all be 50 meters long. So we've got 200 meters of equipment that we need to fit in somewhere without ideally moving anything else. Great Western used 4 overlap carrier wire neutral sections because they wanted to satisfy any possible kind of train configuration. Because if we had a 3 overlap case and we ran a 3-pan configuration through it, there's a chance that we short out the system and join up the phases. Similarly, if you try and run a 3-pan through a 2 overlap configuration, that definitely doesn't work and we will short it out. So for different configurations, you might have a first guess at, if I've got n pans, I'm going to have n+1 overlaps. That way I have guaranteed that I cannot join up the systems. However, if we chose these overlap lengths better, could we get rid of one of the overlaps or reduce, even if we still had 4 overlaps, can we reduce the span length? So we can kind of fit in the pans in all the different spaces so we know that there's always going to be a gap. To do this, we built a tool, we called it the dimensioning tool, and we looked at every different span length combination between 35 and 50 meters, and all the different kinds of configurations of pantographs in the UK, all the different spacing. So effectively, we looked at nearly 9 million different combinations. And we worked out what is the minimal number of overlaps and the minimal length of the carrier wire neutral section. Excuse me. Ultimately, it boiled down to 2 identifier functions. that just told us, is there a pantograph in a span? Is it in 2 spans, and therefore it's causing a bridge? Whatever the maximum number of bridges is tells us the number of overlaps we're going to need without shorting out the system, and what is the minimal out of all of those maximals for all of the configurations will give us the perfect carry Y neutral section effectively. We've got a little animation here, which is the output of the tool. Hands up if you knew you could do animations in Excel. Yeah, we didn't either. Is it playing? No, it's fine. We'll move on. But also, that was based on existing designs. What can we do with the equipment we've already got? Or, is there a novel way of doing it? Can we use conductor rail for a rigid supporting system to hold the overlaps? And that, if we could get it down to 10 meters instead of 200 meters. The issue with a rigid system is if I put a pan against it, it has a massive peaking force. Maximum force for a carry Y neutral section is allowed to be 350 newtons. Our first attempt at one of these was 400 newtons. So we scrapped that idea pretty quickly and designed a ski jump overhead line. The pantograph runs along the bottom wire and then deliberately leaves the wire and rises up to join the next one. So there is a deliberate discontinuity between the 2 wires. So we could make our overlap separating the phases a meter. Or if NOAA is a bit nervous about having a discontinuity like that, we designed a catenary version that is electrically separated, but again, the pantograph comes off the wire because the wire rises quicker than the pan does. But it's also bi-directional running, which the one on the left is not. You could not run a pan that way. Turns out they're not as crazy an idea as you might think. It actually performs better than a rigid version. So the main factors that we can change here are obviously the length of the overlaps and the amount of rise in the contact wire. Moving to shorter overlaps and reducing the rise of the wire gives you better performance. So here we've got the maximum speeds that can be achieved for different combinations of pantographs on different kinds of overlap spacings and height changes. If we reduce the length and reduce the outer running wire height, we can achieve maximum line speed for lots of different kinds of pan spacings. Problem is, I need to have a passing clearance between my pantograph and my infrastructure. The pantograph lifts the wire up by up to 125 mil, and I need a minimum of 200 mil passing clearance. So there is a risk that with 75 mil that I'm going to flash over from the pantograph to the earth bits of the overhead line. That will raise a fault in the electrical sectioning people, and they'll turn it off because they think there's a problem. Now, if that happens once every 10 years, nobody's going to particularly worry about it. If it happens every time a pantograph goes past, then we shouldn't do it. So we looked at some real uplift measurements provided by Atkins, where they sat by the side of half a dozen locations and measured the uplifts as pans went past at lots of different speeds. We did some analysis on this data to kind of get a feel for what is the actual uplift of a real line in real service. Then we plugged this into a probability density function to work out how many pan passages are we likely to see before we exceed the amount of uplift before we're getting a flashover. In the worst case, because we're only worried about the registration arm here, there's obviously no infrastructure to flash over to at midspan. It's every 250,000 pan passages. On the rear pan, it was practically non-existent, but to give an actual number, it was 25 million. So that's all well and good, but how long is it before I've had 250,000 pan passages? Well, we looked at East Coast, West Coast, and Great Eastern main lines. It turns out it's likely to not happen for 120 years. So we're kind of feeling okay that we can do this. And that is my research and what I get up to as a job, I think.
Have we got 1 minute left?
1 minute.
Cool. I'm going to jump all my slides to make up time and just show you one. We were still left with, after all of Sam's work, with where couldn't we validate the model? What specific cases, infrastructure issues out there, couldn't we model? So this led on to this project here. So this looks a little bit like CGI, but it is a real video. It's sped up. It's 20-second video, but it's actually sped up from about 2 minutes. Those wires each one's under about 11 kilonewtons of tension, so you don't want to move them too quickly. But what we're currently building, and this was a small section we built to begin testing at the end of last year. So this was just before Christmas, this video, was a section where we can test with a real test train on a test track, any combo of any issue we could think of, and also validate not only our models, but anyone else's models. So we know even in extreme circumstances, they're still work and valid. So this is our main project for 26 is actually then, 25 is then extending this on to a much longer line. In the end, we're going to have about 1.2 kilometers of this equipment. The little bit you can see there is 150 meters or so of it. So that's our test equipment we're building this year is extending that out. So I think that's it for us on time.
Thank you. Unfortunately,
No time for
no
questions.
time for questions.
We are around, so
Yeah.
feel free to ask.
There is another poster session after the next presentation session. So if you have any questions for Noel or Sam, please go and see them.
Cool, thank you.
Thank you.